Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the next and last speaker in this session, actually before the coffee break, is Mark Polyphase. He's a professor at ETH Zurich, and he will be talking about challenges and opportunities in modeling urban environments.
Okay, thank you, Michael. Thank you for inviting me. So I wanted to talk a little bit about some of the things we've been doing in the last few years. Okay, so this is what we could do already about 10 years ago, and so we are very successful in essentially getting a video, getting some images, and turning those into 3D models. And so we decided to try to push that towards, to use that also to reconstruct 3D urban models, as more and more there's demand to build up these models of the whole world. And so starting from essentially videos, as you see up there, essentially trying to turn them into 3D models. And so we worked hard on setting up a pipeline that we could do this also actually with goals of doing all of this in real time. As we want to model the whole world, we better do it relatively efficiently. And so by leveraging the GPU and so on, we're able to achieve this type of goals. However, there's many challenges that we encountered in this. So here you see the type of models that we obtain when we do that. So essentially we use the same type of structural motion and then in particular dense multi-view stereo. When we actually analyze those models, the median errors are in the few centimeter range typically. However, you see many artifacts, windows are just missing. There's lots of holes because we're missing some data, or we have some uniform regions where we don't quite know what happens. We look at things actually at the edge of the field of view, and we have edges that align with the direction of motion and so on, and so we have lots of ambiguities and things that go wrong. And in particular, discontinuities also in the actual world. It's not just a single nice object we look at from different directions, but it's actually a very discontinuous world with many objects of different types all intermingled. So visually they're a bit less pleasing than we had hoped for. So also let me show you here a little bit of what's actually going on under the hood. So here, two video streams watching a facade, and then here's essentially what we work with. So this is the real-time stereo that we get. It actually works really nicely on most walls and other stuff, trees, other structures, except that we get clearly some problems when we have strong horizontal lines and we drive horizontally past the facade. That's one issue. And then, of course, windows, they really give you strange results. So we try to see what we could use. On the other hand, of course, we're looking at urban scenes. We're mostly interested in the buildings, so that's what we want to do well on. And of course, that's not a generic object. There's actually quite some structure in there. So one of the things we tried to explore was to try to bring in planar priors. Now, there's been a lot of work in the last few years to do Manhattan world reconstructions and apply these type of priors, but typically they've been applied indiscriminately to the whole scene, giving often unpleasant results if the scene wasn't only a cubic building, but actually was a mix of trees and buildings and other things. So what we did here was to first generate an arbitrary number of hypotheses, of planar hypotheses, just from the data, and then at the same time also identify, actually learn both from the image and from the stereo volume here, learn from training data and then infer here from this image what is likely to come from something we want to be as a plane. So in particular, what is likely to come from a wall, or what is likely to come from a window. Even if the window, we even really perceive it as a plane in the original data here, if it looks like a window and it doesn't look like a tree, then we probably really want to just fit whatever the closest plane is to it. And so essentially, and vice versa, when we're looking at a tree or some other organic structure, even if approximately it looks more or less like a plane. Locally, we just want to avoid replacing it by plane. Okay, and so we get this type of results then by writing this in MRF optimization that combines all different terms. We also get much nice consistent planes. Actually here shown in one depth map, but it's actually consistent over the video sequence. So we extend those planes beyond single frame. So here's then a video where you see that at work. In particular, notice that there's multiple times the same color, so actually the plane is extended over from one frame to the next there. So also here, see how it can nicely handle typically the problems with windows and other things. Now, of course, it doesn't quite fill in things behind, in places that we didn't see. And also, this was rather expensive in terms of processing with the MRF optimization. Okay, then as we moved on, we tried to find something that could both be fast, might not be as accurate in geometry, but give us something that would give us essentially closed models that would try to somehow capture a lot of the urban structure. So in particular, in urban buildings and urban structures mostly have vertical facades. So vertical direction is really a preferred direction. And so we essentially tried to look at if we could use just a Heightmap representation to do depth map fusion on. So instead of doing depth map fusion in one of the original frames or from the original viewpoints, we did essentially depth map fusion on a vertical representation, so a vertical Heightmap. Now, of course, if you just do that, then you get, and you have some overhanging structure, you get this type of problems, right? So you have to choose if there's an overhanging structure. If you put the ground at the top of the overhanging structure or on the original ground, you get something with a single layer as on the left there. However, what we can do is actually decide to, based on a model selection and on a per pixel in the Heightmap, make a decision on how many layers we need to do a good representation there. Now, this representation can both be calculated very, very fast. This is actually all running in real time. But it has this very strong regularization because essentially everything on the same vertical structure will vote for the same depth discontinuity, essentially, in this Heightmap representation. And so we get here results essentially at real-time rates on a single PC. So here you see, now the texture here, you see the texture is a bit washed out and the geometry is coarse. This is because we use a reasonably coarse grid and then essentially just project all of the images we have on the same voxels. And that's why you get this washed out effects of the texture. So we could do work on cleaning it up. But you get an idea of, we get now almost perfectly closed models. Things like trees and pillars and so on come out quite nicely. Clearly we have artifacts within the texture there, as you see up. But look at the car, is actually a closed surface now. You get here, even the basketball ring is actually present there. So you get these structures to actually robustly come out of it. So those are certainly not perfect reconstructions, but we actually get very robust reconstructions here. They're quite close to the original shape, up to some noise. So here also then, using a similar type of technique on indoor data. In this case, we have a forward-facing stereo camera, which could be mounted on a robot. It's actually at the Mountain View offices of Honda Research. These are the depth maps, so you see very noisy, lots of missing data and so on. And so then when we do fusion, it's really important to have this strong regularization. And so for a robot, for example, here to navigate in an environment, it's important that it somehow can figure out the environment, even if the data is actually hard to work with. So here, where in the previous work we had every point was calculated fully independently, and you could already see the results were typically quite good. Here we actually have regularization across different elements, and then you also see here that you get essentially a nice flat surface as neighboring pixel elements talk to each other. Actually related to that and prior to that, if you want to do this just from a passive camera walking through an environment or a passive stereo head, it's important that you actually also calculate, of course, the motion of your vehicle or your robot or your platform through the environment. What you see here is a real-time visual SLAM implementation. The video on the top is accelerated 5 times. But essentially, we do a full visual odometry and then detect loop closures and then adjust everything. It runs essentially on a laptop in real time. We don't do a full bundle adjustment, which would be, of course, the perfect thing to do. But we keep essentially a topological metric representation that tries to locally be metric and be globally always topologically consistent, and try to get as good as possible metrically, but make sure to preserve the topology for sure. Okay, so then similar work beyond working with vehicles driving or robots walking around. We've done in the last few years lots of effort on trying to have fully autonomous flying helicopters. So our first generation here was flying autonomously but with markers, so we engineered the environment, but then it was flying fully autonomously, all calculations on board. When then you have your algorithm crash, it's actually a physical crash. So this is actually very challenging. And then what you see here is one of our most recent results where we, now here you see the safety device, of course. So where we fully fly autonomously, in this case, again, all calculations on board and so on, but without a prepared environment. So here, there's even, you can set waypoints, or you can actually even tell the helicopter here, it has a stereo head, and in this case, it will actually detect the wall, and then it will follow the wall and keep exploring the world and model the environment as it goes here. So here you see it fly autonomously, still with a safety rope attached to it. You see the depth maps here. This is all calculated on board. So we have very limited, well, relatively limited resources on board. And so our models are, of course, limited in that sense. But we can actually use it to do real-time online navigation fully autonomously with everything on the device.
Okay.
Yes?
So how long does it run with the battery?
So it's the battery lasts about 15 minutes. The helicopter itself takes about 150 watts to hover, and so our compute platform is essentially the equivalent of a laptop, a Core 2 Duo, and that just adds 20 or so watts, so it's not much of an issue. But yes, I mean, in general, of course, the applications are limited by this currently. Both in those helicopters, as well as actually nowadays in every cell phone or so, is actually there's many interesting opportunities in using these cameras instead of just an arbitrary, photo camera. Is that you have a lot of additional sensors in there. Of course, you have GPS in here, but also very interesting is you, for example, have inertial sensors or gyroscopes in here. And so a lot of the calculations that are expensive and are difficult to get robust can be simplified by using those additional sensors. So here's just an example of something we did, was to use the fact that you can, if you take a picture, then you typically hold your camera still. You have, essentially, if you read out gravity, if you read out acceleration, you get pure gravity vector. And then you can use that to really simplify your relative pose estimation. So for example, here, you can go down from a 10th degree polynomial to solve to a linear thing with 5 points. Or if you go to the minimal solution, it's 3 points, and you get a quartic to solve. Notwithstanding all of this, when we are closing loops in reconstructions, often, except if we have omnidirectional images, but otherwise, we mostly can only close loops when we walk through the same hallway in the same direction. If we happen to walk in a different direction or cross our path, we didn't close loops, and I think most people have trouble closing loops under those conditions. And the problem is really that white baseline matching is still really, really hard. And so one thing that we propose is to really, depending on the scenario, there's now many scenarios where you might be able to do small baseline matching and get several images, for example, from your video sequence locally to get a 3D model. And what we're arguing is that then you should really use that information, build a local 3D reconstruction, and then use that to essentially not have to pay a lot of, essentially pay a high price in terms of trying to get invariants in the image, and do 2D invariant feature extraction here, but essentially go to the 3D surface and extract features directly on that surface. So that's what we call viewpoint invariant patches, so VIP. And essentially, we take your favorite feature detector, but instead of doing it in the image in 2D directly, just extract it straight on the model, on the surface. Now, of course, nowadays with Kinect sensors, this becomes even more relevant. You have now the geometry straight away in many scenarios, and then you can extract also there directly for the, you take the image, you warp it to the surface, and then you extract features in there. So here's an example of how that works. Two different models here on the left and on the right. You see the camera viewpoints are very different. The actual correct matches are this part matches this part here. The green are just the original seek descriptors matching. The red is where we have a fit of scales. So what's interesting is there's a lot of challenges in urban scenes with repeated structures, and I'll come back to that. But in particular here, you have bricks, random bricks matching other random bricks. Well, it's the wrong brick, but it's actually still the right scale of brick. Okay, and so actually you get initial support for the right scale. Then after that, you get initial support for the right orientation, because different bricks on the same wall will vote for the same orientation, etc. So that way we can actually handle here a massive amount of outliers. 90% of the features initially are outliers, and still trivially essentially get the result, the correct result out. If you try 5-point on this, just forget about it. So we've also tried to use that in scenarios that are asymmetric, where we have maybe a 3D database in the background, but we just get a single picture as a query image. And so in that case, what we do is try to rectify the query picture. So in urban environments, you have a lot of structure. And so typically, it's not very hard to rectify. You could also use potentially sensors for that, if you have them. And then extract features on rectified facades. And then, of course, you do the same thing in the in your database. You actually also store those features for rectified images. And then here also, you can actually take advantage of that and match between the query image, the rectified query image, and your database, and get lots of matches. And here also actually exploit the fact that scale should be consistent. X and Y translations we verify separately. Notice that, for example, here there's a repeating window here. And that's why we here in the X direction get secondary peaks here for the other windows matching, so the incorrect windows matching. So that way we can get, I think it's 50 to 80% retrieval from a single picture where we are anywhere in San Francisco, based on a database of 1.2 million images. And this actually worked together with Nokia and Navtec and Stanford, and there's actually a test available online and a benchmark that you can participate in. So here's another application of these kind of things, of capturing these representations. Here, just an image-based representation on the device, so where we align it with a ground plan, and then can dive in, essentially. Let me show you, this is all running on an Android phone, so then you can walk around this. And of course, the idea would be you take a picture and you ask, okay, where am I, and tell me where to get to that auditorium or something like that in a complicated building. And so we've done some work on that, but it's actually very challenging. And the reason is the following, is because in such a building, it's very symmetric. A lot of the spaces look roughly the same, different floors look the same, etc. That's actually a problem we've also encountered on the outside of buildings. This work here with Christopher. So where what you see here is images that are actually incorrectly matched. However, we did everything we had to do. We did geometric verification, so matched features, did geometric verification, and we get a lot of support. So most structural motion algorithms from here will say, okay, I get 200 matches, 300 matches correct, this must be correct. And then they don't question this anymore, and they just put it in their structural motion. Bundler or other techniques will just do that, and then somehow they fail then to give good results coming out of it. So what you get is, essentially between all those pictures, if you have this collection of pictures, you will get all the red dots there are different pictures, they're the nodes, and then the edges essentially are verified geometric relations between them. And so you get a lot of those, but some of those are wrong. Some of those are matching this side of the facade to that side of the facade. If you let it in your structural motion algorithm, it just blows up and you don't get results. You get results that look like this or so. So what we realized that you could use is that if those are actually meaningful geometric relations, whenever you walk along a loop, you should actually be able to close your loop also geometrically. So in other words, if I walk around the room and I get back here, my translations should accumulate to 0, and also my rotations should accumulate to a multiple of 360. And so that's something you can verify. If I match this facade to this facade here, only 180 degrees apart, then I get a loop that only does 180 degrees. Then I know something's wrong. Okay, so essentially, you get by just trying out and sampling random loops, you can essentially detect that there's a few places where there's inconsistencies accumulating. And then you can start an inference where you actually try to find what's the smallest number of links that I have to cut to essentially get rid of all my inconsistent loops. And so by doing so, you can actually quite nicely identify a lot of those problems, get rid of them, and then get nice reconstructions coming out of it. Okay, so that's what we did 2 years ago with Christopher. And then after a while, and this is actually very close to what Michael was talking about earlier, we realized, well, why are we throwing all those nice links away? Knowing that this side of the building is almost exactly the same as that side of the building, we should not throw that away. We should actually make use of that. And so we started exploring actually keeping track of all those links because those are definitely non-random occurring events, and they can essentially be used to make a much tighter reconstruction. So in particular, if at the end you do a bundle adjustment, you can see all of those copies where you detect that this side looks exactly the same as that side. Or of course, now that we're actively looking for those relations, we'll also look for symmetries. We never get confused by symmetry because you'd have to mirror all your descriptors or so to get the wrong matches. But of course, once we're looking for those relations, we also look for those. And then essentially we get all these type of links between parts of the geometry that are non-local, but that essentially are virtual loop closures. And so they can really tighten our 3D model a lot. And also allow for things also, as Michael was talking about, where you can do completion this way. You might only have one feature detected here, but it's reconstructed in 3D here, so that you can hypothesize it and then verify it, et cetera, so you can actually start doing nice things. Also, you do get all these symmetry planes and other relations that give you some nice, sometimes compact description of your models, and they also tell you something about the dominant orientations in your building, et cetera, et cetera. So you get a lot of nice things coming out of this. So we had already been interested longer by this type of symmetries and repetitive structures. Here in particular on facades, we had been looking at directly detecting them on facades by detecting dominant orientations of the facade, rectify them, and then extract repeating structures and detect actually the size of the repeating element. So again, very similar to what Michael was doing, but directly in a 2D image and not on a 3D model, which has some additional challenges, of course. But what you see is what we also realized. So you can extract those. You could use these for different things, for potentially extracting or using an architectural grammar to explain those images, or maybe even extract grammars. You can, of course, do shape from symmetry or repetition. So here, if we get, essentially we detect that something is 5 times repeated every time from slightly different viewpoint, you can do reconstruction from that. Something that is really nice also is you could see here, these regions that we extract here, as we could see this whole system as an invariant region extractor, a very fancy one. But on urban scenes, actually a very powerful one. And that's actually illustrated here. We did a test on the Zurich building data set. This was suggested by one of the reviewers of our paper, which has essentially 200 buildings, and for each of them 5 images. And so what we did was to use those features here to, given one image, to try to retrieve the corresponding images of the same building in Zurich. What you see here, those 2 curves here, this is what SIFT is doing with the 10 and 100 largest features that you find on those images here. And then what you see here is essentially what we're getting with different settings or different choices. But in particular, what we do is we take one of those elements here and describe it by histogram of gradient type of representation, similar to, but then on an 8x8 grid instead of a 4x4 grid. So it's like SIFT, but on a bigger grid because it's larger elements and they're more descriptive. And so that gives us about 75% with a single feature, actually. 75% retrieval for the first and so on, and it goes down for the fourth corresponding one. So the last one, we're still at above 50% correct retrieval. So it's actually a very powerful feature that you get in this case for urban scenes. Other things you can do with symmetry also, just symmetric buildings, get depth reconstruction. then of course something important in urban scenes is that they're not static. Depending on the time scale you look at, there's changes happening. And you could of course start somehow rebuilding every time a new model if you do that. But that's clearly not what you'd want to do. You'd want to know where some change took place. And so here we propose a very simple approach where you're given a reference model. So here image-based one, but it could be laser-based also. And then you get some images, and you want to verify if the current images you get are still compatible with the geometry of the previous model. In a way, what we use is something very similar to what we do with plane sweep stereo, where we hypothesize all the different depths. Here in this case, well, we don't have to hypothesize all kinds of different models. We actually have a model, we have one model hypothesis, so let's just try that one out. So we project from one image on the model, project back into the reference viewpoint, and then we can compare images. If everything's still consistent, we have no errors, so dark image. If we have some updates, then we start seeing some differences, and so that gives us hints that something has changed here. So here we see some results. So of course, on top of that, many changes might be relevant, so you can run all your favorite detectors for the features that you might not care about, like people, cars, vegetation. In an urban setting, those are not relevant. Of course, more generically, you might just, if you have a vehicle like a trash car so that drives by every week, you might just look for non-transient changes. So if something is parked here or there, if it changes every time, it's probably not so relevant. But if something has changed and then stays changed forever, it's probably relevant. Okay, so then while we were doing all this structured capture, others were actually trying to do capture from unstructured data collections, like Alyosha, or also, of course, Noah Snavely and Steve Seitz were doing here for taking large photo collections online and trying to work with that. So here, Rome, there were 3 million images. Steve, I think, processed about 150,000 in 24 hours on 64 machines. We decided to give it a go and try to run everything on one PC in 24 hours, the whole 3 million image data set. And so here's some results of that. So essentially we used GPU, a lot of GPU algorithms. We actually had our PC. Okay, our PC was a $10,000 PC and had essentially 4 GPUs in there, and needed 2,000 watts to boot, which was also not so trivial. But anyway, so we first cluster images together to avoid actually full pairwise comparison between our 3 million images with our 3 million images. So we first cluster them based on appearance, then within cluster do comparison, and then from cluster representative to cluster representative. And that allows us to give a quite good set of matches. We're able, out of 3 million images, to align to each other about 300,000 images we can actually localize or combine, attach two clusters like this. And then also, as we had still some time left, we decided to also do dense modeling at the same time. And for this, we actually use our Heightmap model. And so here, in this case, our model selection would select sometimes up to 7 different height levels here for the Colosseum, for example. Of course, those are approximate models. I told you they're washed out here. Particularly, they look essentially like taken in overcast sky. That's because we take the average of all possible illuminations we get. So Jan is from Germany, so he also tried he also tried it on Berlin, worked also. Okay, so here you see the model. So you see it's very blurred, but as I said, this is just based on blurring on all those images together with the coarse geometry. It might be, I don't know. Okay, so anyways, yes. So I'll finish with this here. So something else we explore is beyond just capturing 3D models. We also wanted to explore, okay, what if you now have an event? So this is actually very, very related to what Jan was talking about earlier. What if we have some interesting event? People all take out their cell phones, start recording from their viewpoint. How would you want to explore this data? Right. So here's a system at work. Essentially, what we wanted to try to do is to let you transition from one viewpoint to the other. So you're always embedded in the video, but then as you go from one video to the next, we wanted you to preserve the spatial context, and so not have an instant switch from one viewpoint to another, but really somehow naturally transitioned, as much as possible naturally transitioned. So this goes in 2 steps. No details, no time for that. But essentially a lot of offline processing to calculate as much as possible out of the videos and enable then an online interactive navigation system where we do image-based rendering or video-based rendering and recombining all of the data we've calculated before in real time then, interactively. So here's then the system in action. So you can try this out for yourself. You can actually download the player and the data, and then you can actually interactively navigate yourself. Here we only have 3 video sequences, so it's very wide baseline. And so we still can generate reasonable transitions. You get spatially localized sounds for free here.
And he's going to do something with flame, and it's all going to be very exciting. Check the blade. I gotta go, yeah? Check the blade, folks.
So of course there's many challenges here. You need to localize your video camera. At every point, it's a handheld camera, so you can move around. So we need to localize for every frame versus the general reference frame. We need to do segmentation of the foreground character. So here is our flip actually, right? But that's because we were from 2 sides. Okay, so that's essentially...
And I thank you all personally for watching the show. Thank you very much. Thank you.
Okay, so that's it. So, yeah. So, okay, in conclusion, there's clutter and reflective surfaces as challenges. We're actually currently working at really capturing full reflective surfaces, like the normal maps of windows and stuff like that, but that's future work. I mean, that you'll see at some other point. Repetition, symmetries, dynamic transient parts are all big challenges, but often they also correspond to opportunities if you can exploit them properly. Also, having cameras with sensors is really nice and offers interesting opportunities, and also the fact that there's cameras now everywhere. Okay, I'll leave it here.